Hi, data scamps and data champs. Today we're kicking off a crash course on Docker and Kubernetes, two essential tools for modern DevOps and scalable software development. This video is taken from a series of courses on DataCamp. You'll learn the foundations of containerization and virtualization, how to build and manage containers with Docker, and how to orchestrate the containers at scale using Kubernetes. You'll cover everything from Dockerfiles to multi-container setups using Docker Compose and see how these fit into data engineering and MLOps workflows. If you're ready to take your DevOps skills to the next level, please like, subscribe, and check out the full track in the description below. Happy learning!
Hi, my name is Julia, and I will be your course instructor as we dive into the conceptual foundations of the modern tech stack of Docker and Kubernetes. Virtualization and containerization are important technologies that I use in my professional life as a consultant in artificial intelligence, and I'm excited to introduce them to you. While the first chapter focuses on defining and comparing containerization and virtualization, the second chapter focuses on the application of both technologies and how they relate to Docker and Kubernetes. As a teaser, we might even get our hands a little dirty. Let's dive right in by defining virtualization. In our daily lives, we use personal computers such as laptops and smartphones. Since both examples are tangible devices, we can also call them physical machines. In the world of technology, servers play an important role. Servers are specialized computers that serve other computers, also called clients, on a network, performing tasks such as hosting websites or running data analytics. Just to refresh our memories, a computer system consists of hardware, such as the central processing unit, storage, motherboard, and software, such as the operating system and application software. Things get a little tricky when we need our computers to do more than one thing at a time. That's where physical machines have the following limitations. They can be expensive. More tasks often mean more hardware, which means a bigger investment in buying and maintaining the equipment. Maintaining multiple physical machines can be a hassle. Updates or repairs require downtime, which can interrupt important work. Physical machines can be inflexible, especially when it comes to scaling. When a machine needs more resources, you have to replace entire hardware components, which can be a complex and time-consuming process. This is where virtual machines come in. Instead of adding more physical hardware, we can create virtual machines. A virtual machine, or short VM, is a simulated computer system inside another computer that has its own operating system and applications. Multiple VMs can run on the same host machine. This is the physical computer that hosts multiple VMs. And each virtual machine operates independently without interfering with other VMs. VMs offer advantages over physical machines. We can get the most out of our hardware by running multiple VMs on a single host machine. This maximizes resource utilization, resulting in cost efficiencies and sustainable usage. VMs can upgrade their hardware without having to purchase additional physical hardware, as long as the host machine has sufficient resources. VMs on the same host are completely isolated from each other, preventing the spread of potential threats between them and increasing security and stability. With VMs, different operating systems can run seamlessly on the same host machine. Simply put, virtualization is the process of creating a virtual version of a computing resource. There are different levels of virtualization. The most advanced level is the virtualization of an entire computer system, including both hardware and software. This results in a VM and is also called full virtualization. Other levels of virtualization include virtualizing a specific computer component, such as the operating system or storage, which does not result in a virtual machine. Next, we will explore another level of virtualization. Stay tuned. As we learned earlier, there are different levels of virtualization. In addition to virtualizing an entire computer, we can also virtualize certain computer components. Let's learn about virtualization at the operating system level, also known as containerization. Since we will be using the term environment a lot throughout this course, let's get our definitions straight. In this course, environment refers to the system that surrounds an IT application, including the operating system, or short OS, hardware, software, and other resources. OS-level virtualization involves virtualizing the operating system itself, rather than the entire computer. This means that we don't virtualize the underlying hardware or the OS kernel, which is the core component that facilitates communication between software and hardware. Instead, we create virtualized, isolated user spaces that interact with the host's non-virtualized OS kernel. These user spaces are dynamic areas where user-level applications operate, and the OS kernel allocates hardware resources to them as needed. As briefly mentioned previously, OS-level virtualization is also called containerization because the isolated user spaces are also known as containers. Containers provide an isolated environment in which to run an application. It contains everything needed for the application to run smoothly, such as the source code, dependencies, and configurations. So the definition of containerization is twofold. First, containerization is virtualization at the operating system level. Second, containerization is the process of packaging an application and its dependencies into a container with its own environment managed by the OS kernel. Let's consider the characteristics of containers. Containers allow multiple applications to run reliably on a single host operating system without requiring a dedicated operating system for each application. Each application is packaged in its own container, which means that each application has its own environment and does not interfere with the dependencies of another application. Developing applications in containers also makes it easy to keep track of which dependencies are needed for an application and which are not. When comparing application development in containers to physical machines, containers offer the following advantages. First, they provide isolation, meaning they do not interfere with other processes running on the same host machine. For example, if one application crashes, it won't affect others running in separate containers on the same host. Second, containers are highly portable and reproducible. Because they contain everything needed for the application, they're easy to move and behave identically when run on different host machines. Finally, containers have fast startup times. Unlike applications running on physical machines, containers don't need to load an entire operating system. This is critical for highly available applications or deployments that need to scale quickly. Now let's compare virtualization and containerization. First, let's review both terms. Virtualization is the process of creating a virtual version of a computing resource. Full virtualization creates a virtual machine, a simulated computer system inside another computer. Containerization is virtualization at the OS level. It packages an application and its necessary dependencies into a container, an isolated environment with everything needed to run the application. There are several software tools available for both technologies. One of the most popular tools for building, distributing, and running containers is the Docker platform. For orchestrating containers, that is, automatically managing and coordinating multiple containers, Kubernetes is a common choice. We will talk more about container orchestration in the next chapter, so stay tuned. Virtualization software, such as Oracle VM VirtualBox or VMware, helps create and manage virtual machines. Let's dive into use cases of full virtualization. Full virtualization is often used to make better use of existing servers by running multiple virtual machines on a single physical server. Organizations have a variety of reasons for keeping legacy applications alive. With virtualization, legacy hardware and software can be emulated by virtual machines, even when running on modern infrastructure. Let's take a look at some use cases for containerization, OS-level virtualization. Containers provide a way to isolate an application from its environment by packaging the application in a container. In addition to packaging an application, an organization may be interested in packaging each service or component of an application into its own container. Structuring an application as a collection of services is known as a microservices architecture. The benefits of microservices include the ability to use different technology stacks for each service and to scale services independently. As we briefly mentioned earlier, container orchestration is the technology for managing and coordinating the deployment, scaling, and management of multiple containers. Orchestrating containers is similar to conducting an orchestra. We direct containers to perform different tasks, just as we direct musicians to play different instruments. This table provides an overview of where containers or virtual machines outperform physical machines. Let's take a closer look at some of the advantages. Because virtual machines emulate the entire hardware, a VM provides stronger and more secure isolation than a container that shares the host OS kernel with other containers. In the event of an attack, access to the host OS kernel results in access to all containers on that host. Because containers share the same operating system and therefore take up less space than virtual machines, containers can result in lower overhead costs. Because of their light weight, containers are more portable and scalable than virtual machines. On the other hand, virtual machines provide the flexibility to run multiple operating systems on the same host machine, and even support legacy applications on modern hardware. As you can see, each has its own advantages, so depending on the use case, we need to choose the appropriate approach. Let's continue with Chapter 2 and start with containerization with Docker. To recap, containers provide an isolated environment in which to run an application. They contain everything needed for the application to run smoothly, such as source code, dependencies, and configurations. Docker is the go-to choice for containerization and is open source, meaning its code is freely available for anyone to use, modify, and distribute. Docker has a large user base because it has revolutionized and standardized the way we use containers. According to Stack Overflow, Docker is one of the most used and popular tools out there. Managing the life cycle of containers, Docker is a software platform that provides tools for building, distributing, and running applications using containers. Here's a brief overview of important components of Docker's architecture. Let's go through each of them one by one. To get started with Docker, you'll want to install Docker Desktop. It's a desktop application available for Mac, Linux, and Windows. Docker Desktop provides a simple graphical user interface, also called a GUI, for managing your containers, applications, and images. It also includes the Docker engine. The Docker engine acts as a client-server application. Users can trigger Docker actions through the Docker client. The most common way to do this is through the command line interface, also called the CLI. The CLI is the interface where we enter text commands for the computer to process. Certain commands can also be invoked through Docker Desktop. Client requests are received by the Docker daemon. The Docker daemon is the core service responsible for building, running, and managing Docker objects. It needs to be running whenever you're using Docker. There are two main Docker objects: images and containers. To build an image, you start by writing a text file called a Dockerfile. Like a recipe, it contains a series of instructions for building a container. You use the Dockerfile to build the blueprint for your container. This blueprint is called a Docker image. Once you have a Docker image, you can use it to create a container. To make this clearer, here is an analogy. Imagine a company that builds prefabricated houses, meaning every house is the same. Their Dockerfiles will be the blueprints for different houses. Their Docker images will be the different house models that a future homeowner can choose from. And their Docker container will be a constructed building based on a house model. Because this company builds many of the same houses, the same house models, the Docker images, are used multiple times to create multiple houses, multiple Docker containers. Finally, Docker registries are centralized locations for storing and managing container images. For example, Docker Hub is a popular public registry provided by Docker. Now that we're familiar with Docker and managing individual containers, what if we're dealing with applications that require multiple containers? This is where container orchestration comes in. Orchestration is the automated management and coordination of multiple components or services, such as containers. The tool used for orchestration is called an orchestrator. And container orchestration is the orchestration of containers. To use an analogy, container orchestration is like having a conductor to keep an orchestra in harmony, except that the orchestra is made up of containers. Container orchestration simplifies the management of large numbers of containers. It ensures that multiple containers work together effectively to do what they're supposed to do and efficiently with the least amount of resources. Container orchestration uses declarative programming, a style in which we define the desired output rather than describing the steps to achieve it. Developers write a configuration file that specifies details such as where to locate container images, how to establish communication between containers, and how to allocate container storage. The container orchestrator uses this config file to automatically achieve the desired setup. So why use container orchestration instead of manually managing containers? While manual management offers full control and customization, and may be a better choice for small applications, container orchestration offers many advantages. Container orchestration makes it easy to scale containers on demand. Imagine you've built a web application and suddenly the number of visitors increases. You need to quickly scale the application to handle the increased traffic. This includes both horizontal scaling, where containers are added or removed, and vertical scaling, where computing resources, such as memory, can be dynamically adjusted for specific containers. This flexibility ensures that applications can seamlessly handle varying levels of traffic or resource requirements. Another key benefit of container orchestration is automation. By automating tasks like resource allocation, developers can save valuable time and improve productivity. This allows teams to focus on more strategic initiatives instead of repetitive manual tasks. In addition, by dynamically allocating resources based on application needs, organizations can reduce unnecessary computing costs. Finally, container orchestration improves application performance by automating scalability and availability. In the event of problems or failures, orchestrators can automatically restart or replace containers, minimizing service downtime and ensuring uninterrupted service delivery to users. However, It's important to note that implementing container orchestration, like most technologies, comes with its own set of challenges. One of the primary challenges is the complexity of the technology. However, as teams gain experience and expertise, they can effectively overcome these challenges and gain the many advantages of container orchestration. So, where is container orchestration useful? First and foremost, it's valuable in scenarios like microservices architecture, where large applications are broken down into smaller, more manageable services, each running in its own container. It's also critical for handling applications with changing requirements, ensuring that peak usage times don't result in downtime, and automating pipelines across domains such as data engineering, machine learning, or software development. Finally, there are several tools available for container orchestration, including Kubernetes, Nomad, Red Hat OpenShift, and Docker Swarm Mode. Each tool has its strengths and is suited to different use cases, so it's essential to choose wisely based on specific requirements. Previously, we touched upon Kubernetes. Now, let's get a little more detailed about how container orchestration can be applied and take a close look at Kubernetes, the de facto container orchestrator for many organizations. Kubernetes, often abbreviated as K8S with 8 letters between K and S, is a software platform that simplifies and automates the deployment, scaling, and management of containerized applications. Originally developed by Google and later open-sourced in 2014, it is now maintained by the Cloud Native Computing Foundation. According to the foundation, most organizations nowadays use or evaluate using Kubernetes. Kubernetes groups the containers that make up an application into logical units. More on that soon. It's also important to note that Kubernetes operates as a distributed system, meaning that its various components are spread across different machines. These machines can be virtual or physical, hosted either in the cloud or on-premise. Here's a quick overview of important components of the Kubernetes architecture. Let's go through them one by one. A pod is the smallest deployable unit in Kubernetes, consisting of one or more containers that share the same computing resources. Each pod serves as a unique environment in which applications run. One or more pods are grouped into a node, and each node serves as the host on which the pods run. Nodes are the smallest unit of computing hardware in Kubernetes, representing a pool of computing resources, whether virtual or physical, hosted in the cloud or on-premise. Rather than being actual custom machines, nodes abstract machines, so any node can be easily replaced with another node, and everything will work the same. A specific pod does not always run on the same node. This is where the control plane comes in. The control plane manages nodes and pods and ensures efficient resource allocation by smartly assigning pods to available nodes. The control plane is also known as the brain of the cluster. A Kubernetes cluster includes all previously mentioned components and is a group of up to multiple thousands of nodes. In a cluster, the resources of individual nodes are pooled together and form a more powerful supermachine. This supermachine is the cluster. One benefit of the Kubernetes architecture is the convenience of not having to worry about which specific machine or node in Kubernetes is running a particular application. Kubernetes takes care of that for you. While Docker is the go-to containerization platform for developers, Kubernetes actually uses a slimmer container engine, such as Containerized, to efficiently orchestrate large numbers of containers. Why is that? While Docker is optimized for developer experience and ease of use, Kubernetes is optimized for efficiency and scalability. So while Docker shines with its user experience when dealing with one or a few containers, Kubernetes is optimized for speed when dealing with many containers. To finish the course, we will run our own Docker container. First, let's review some key Docker terms. The Dockerfile is a text file that defines the contents of a Docker container. The Docker image is the blueprint for a Docker container. We use the Dockerfile to build the Docker image. The Docker container is an actual instance of a container based on the Docker image. To avoid confusion, let's distinguish between Docker instructions and commands. Docker instructions are the building blocks of a Docker file that detail how to build a Docker image. In contrast, Docker commands are executed through the CLI. They are sent to the Docker daemon to manage Docker objects. Let's examine the format of a Docker file. Each instruction in a Docker file can begin with a comment describing the details of the instruction, followed by the instruction itself. The instruction starts with its command and is conventionally written in uppercase. Then follows the argument that is conventionally written in lowercase. Instructions in a Docker file are executed in the order in which they are written. A Docker file can start with either metadata, comments, arguments that will be used later in the Docker file, or the from instruction. Here is a quick overview of important Docker instructions. Let's go through each one. The from instruction refers to an existing image that we want to use for our application. The argument defines the image to build on and serves as a starting point. This image can be further customized with subsequent instructions in the Docker file. The copy instructions copies files or folders from a source, first argument, to a destination, second argument, within the container. This is useful for files that are needed for subsequent Docker instructions. A dot represents the current execution folder. The example shown would copy the contents of the folder where the Docker file is being executed to the container's main folder. The run instruction runs a command, specified as argument, within the container, similar to how we would run a command in our computer CLI. The entry point instruction defines the container's default behavior by specifying a command to run at container initiation. It defines the primary purpose of a container. Here's an example of a Docker file and how the Docker instructions are assembled. It starts with a from instruction by defining an image on which to build on. It continues by copying some files into the container with a copy instruction. It uses the run instruction to run a command inside the container. And finally, the entry point instruction executes the primary purpose of the container. Finally, let's look at two essential Docker commands, docker build and docker run. The docker build command builds a Docker image from a Docker file. The argument specifies the context. The context is the location where the Docker file must be when the command is run from the CLI. The docker run command creates and runs a Docker container from a Docker image. The argument specifies this image. All Docker commands are executed through the CLI. Don't worry if you're not familiar with the CLI. We'll provide you with the necessary commands for the interactive exercises. Congratulations! You have completed the course. In Chapter 1, we learned about the differences between containers, virtual machines, and physical machines. In Chapter 2, we delved into the practical applications of containers and their orchestration, focusing on Docker and Kubernetes. We learned about the differences between virtualization, full virtualization resulting in a virtual machine, and containerization, OS-level virtualization resulting in a container. We also looked at containerization with Docker and discussed key components of its architecture. We learned about container orchestration and its application with Kubernetes, looking at key components of its architecture. Finally, we learned important Docker instructions and the Docker build and run command. Hungry for more? Virtualization and containerization are important technologies used in the cloud. If you want to learn more about cloud computing, take the non-coding course on cloud computing. Finally, you interacted with the CLI. Want to get better at it? Take DataCamp's course Introducing Shell. Want to learn more about Docker and Kubernetes? Great, we got you covered. Continue with DataCamp's interactive courses that further introduce you to Docker and Kubernetes. I hope.
Welcome, my name is Tim and I'm a software engineer. In this course, we'll give you hands-on experience managing, running, and creating containers. Let's start by seeing how to use Docker to start, stop, and inspect the output of containers. We'll be using the command line extensively, and some familiarity is needed. Commands like nano will be used with only a brief introduction. Therefore, please take the prerequisite course if you're not already familiar with most shell commands here. The Docker command line interface, or CLI, allows us to send instructions to the Docker daemon, which manages containers and images. The basic command is Docker. To start a container, we need an image, which acts as a blueprint defining what will be available in the container. For example, the Ubuntu image contains the full Ubuntu OS. When we start a container from this image, we get a running instance of Ubuntu that we can interact with via a shell. If we want to start a container from an image, we can use the docker run command, followed by the image name. To start the Hello World image, we would use docker run hello world. By default, Docker starts a container and shows you its output while it's running. When we run a Hello World container, it prints an explanation of how the container works and then stops. When an image is created, the creator can choose what happens when a container is started from the image. For example, the creators of the Hello World image chose to print out text and then make the container stop itself. Another example is the Ubuntu image. When starting an Ubuntu container, it will start and then shut down immediately without printing any output. Its creators decided it didn't make sense to output anything specific by default. Instead, the Ubuntu image is intended to be used with the -it flag. Using docker run -it followed by an image name, we can start a container and simultaneously get an interactive shell in this container. If we do this with the Ubuntu image, we get a new shell inside the new container. The shell gives us access to a clean Ubuntu environment isolated from our host machine because it runs inside the container. Once we want to exit the container, we simply use the exit command, which returns us to the host machine and then stops the container. We saw a container that just prints text and one that makes more sense to use interactively. A third type of container processes data or can be interacted with in some way externally. For example, a container with a database like Postgres. These are run using docker run -d for detached, followed by the image name. These containers run in the background without printing their output to our shell. The docker ps command allows us to see any running containers. The first column contains the container ID, uniquely identifying each container. The docker stop command can be used to stop containers we no longer need. Here is a summary of the new commands you can refer to when completing the exercises. Now that we know how to run containers in various ways, interactively or in the background, it is time to learn some commands that will simplify our life when working with containers. When there are only a few containers, it's easy to find them in the list that docker ps returns. However, if you're working with lots of containers, it can quickly become challenging to identify the right one. To solve this, the docker run command has a name flag that allows us to name a container. The name then shows up in the last column of the Docker PS output. Here, we created a container from the Postgres image and called it db_pipeline_v1. For any commands that require us to specify a container, we can use either the container ID or the container name. For example, in exactly the same way we could stop containers using their ID, we can use their name in Docker stop. When using Docker PS with so many containers that even naming them doesn't allow us to find them, we can use Docker PS with the F for filter flag to find a specific container. For example, Docker PS-F followed by, in quotes, name db_pipeline_v1. This will show you only the details of containers with the name you specified in the filter. Now that we know how to find our running containers, it will also be useful to see their output, for example, to debug any issues. To look at the output a container has generated, we can use the docker logs command followed by the container ID. Most containers quickly generate a lot of output, so you'll often have to scroll through the result of docker logs to find what you're looking for. If instead you want to follow the logs your container is generating in real time, you can use docker logs together with the F for follow flag. You will see any logs the container generates live. Even though Docker PS also has an F flag, the Docker PS flag allows us to filter. When working with Docker logs instead, the F flag has another effect, allowing us to follow a container its logs. After using Docker logs, you will see the output of a running container until either the end of the logs or until you press Ctrl+C to exit the log view. Previously, we learned how to stop containers. However, a stopped container is not fully gone. The stopped container still exists and is occupying some space on our hard drive. To fully remove an already stopped container, for example, because we want to reuse its name, we use docker container rm followed by the container ID to remove the container. Here is a summary of the new commands we just saw that you can refer back to when completing the exercises. Until now, images have been made available in the exercises when you need them. In practice, images are either custom-made or downloaded from Docker Hub. Docker Hub is a registry of community-made Docker images. In other words, it's a website from which we can download thousands of pre-made images for all kinds of use cases. For any common use case, we'll find an image on Docker Hub. Downloading an image from Docker Hub is called pulling an image. The command to pull an image is docker pull, followed by the name of the image you want to download. For example, you can download the Hello World, Postgres, and Ubuntu image from Docker Hub using docker pull. When pulling an image using just the image name, we will always get the latest version available of the image. We can find older versions of an image on hub.docker.com. The example you see here is for the Ubuntu image. To pull a specific version, we use docker pull, image name, followed by a colon and then the image version. A version can be a number, some text, or a combination of both. For example, if we want the 22.04 release of Ubuntu, we can use docker pull ubuntu colon 22.04 or colon jammy. Now that we know how to pull images, we need a way to view the images we have available on our machine. For this, we have the docker images command, which will give us a list of all available images and tags. It will also tell us when the image was created, the size of the image on disk, and the image ID, which is a unique ID to identify the image. Docker only has a limited amount of space it can use on our disk. Previously, we saw how to remove containers using docker container rm. Similarly, we can use docker image rm to clear space for more containers and images. A container is a running image. A side effect of this is that you can only delete an image once there are no more containers based on it. If we try to delete an image for which we still have a container on our system, we'll get the warning you can see at the bottom of the slide. This error message also includes the container's ID based on the image we're trying to remove. We can use the docker container rm command to remove the container, after which we can remove the image. It's common to have multiple containers based on a single image, which can make it a tedious task to one by one remove all containers before you can remove an image. To more easily clear all stopped containers, we can use docker container prune. Then, we can use docker image prune -a to remove all unused images. The A flag, which stands for all, makes it so that unused containers are removed and not only dangling images. A dangling image is an image that no longer has a name, because the name has been reused for another image. This frequently occurs when creating our own images. For example, if we create an image called test-SQL, but we find a mistake and change our image slightly, the previous test-SQL image will then become dangling, as our new fixed image now has the test-SQL name. Here is a summary of the new commands we just saw, that you can refer back to when completing the exercises. In the previous lesson, we learned about the official Docker Images registry and how we can pull images from it. This is just one way images are distributed. Now, we will learn how to share images with just a few people or a broader community, either by sending Docker images like you would send any other file, or using a Docker registry server. First, we'll have a look at private Docker registry servers. The Docker organization maintains the official Docker Images registry. Other Docker registries work the same way, but are under the control of another person or group. This means there are no guarantees that the images will work or are safe to use. Images from any registry other than the one from the official Docker organization are easily recognizable because their name starts with the URL of the private Docker registry they come from. For example, the image we see here comes from dockerhub.myprivateregistry.com. Downloading or pulling an image from a private registry is also done using Docker pull. Because the image name includes the Docker registry URL, the image will automatically be pulled from the correct registry. For example, to pull the previously mentioned image, use Docker pull followed by the full name of the image. Here too, we can append a colon followed by the version. Now that we know how to pull images from a custom registry, let's look at how to upload or push an image to a Docker registry. The command for this is docker image push followed by the image name. To push an image to a specific registry, we only have to make sure the image name starts with the name of the registry you want to push to. We can do this by renaming the image using docker tag. For example, if we have the image classify_spam v1 and we want to push it to docker.myprivateregistry.com, we would use docker tag followed by the image we'd like to rename and then the desired new name, including the URL of the private registry. After renaming the image, we can use docker image push followed by the image name to push the image to our private registry. While the Docker official images can be pulled without authentication, anybody creating a private Docker registry can make it private and require authentication. The standard way to secure private Docker registries requires users to log in. We do this with the docker login command followed by the private registry you want to authenticate for. For example, docker login dockerhub.myprivateregistry.com. The URL we authenticate for should be the same as the URL we put in front of an image name. If instead of using a Docker registry, we want to send the Docker image to just a few people, it can be easier to send the image as a file. Use the save command to save a Docker image to a file. This will create a minimized file which we can then share like any other file. We can pass the desired file name to the save command using the -o flag. To load the file, we use the load command, passing the file name using the -i flag. Here is a summary of the new commands we just saw that you could refer back to when completing the exercises. Now that we know how to work with Docker images and containers, it's time to create our own images. Docker images are the recipes or blueprints for Docker containers. To create this blueprint, we must write down a list of instructions in what is called a Dockerfile. A Dockerfile is a text file containing all the commands we would run in the command line to install the software we need, with the addition of some Docker-specific syntax. Conveniently, this file should be called Dockerfile for Docker to be able to find it. Just like when we would follow a recipe, Docker runs the lines in a Dockerfile from top to bottom. The first line in the Dockerfile is always the from instruction. This instruction indicates to Docker which image to start from. We can base our images on any other image, Postgres, Ubuntu, another image you made yourself, or even the Hello World image. As with pulling an image, if you want to start from a specific version, you can specify the version right after the image name, separating both with a colon. With the from instruction, we can create the most basic Docker file. We can then create an image from this Docker file using the docker build command. The docker build command is followed by the location of the Docker file we want to build. If our Docker file is in the current folder, this is simply a dot. When running docker build, in the last line of the output, we can see the ID or hash Docker assigns the new image. The hash starts by indicating its type, SHA-256 in this case. This is followed by the unique hash, which starts with A67F for the example on the slide. If we want to give our image a more recognizable name, we can use the T for tag flag, followed by the name we want to give our image. If we also want to give a version to our image, we can add a colon and the version after the image name. In both cases, we end the docker build command with a dot, indicating our Docker file is in the current working directory. Once Docker has successfully built our image from our Docker file, we can run and use our image just like the images we downloaded from Docker Hub. Now that we can create a very basic image from a Docker file, the next step is to start customizing our image. To customize our Docker file, we will use the run instruction. The run instruction allows us to run any valid shell command while building an image. To make an image that runs a Python data analysis, we start from the Ubuntu image, which has Ubuntu installed, by specifying the from Ubuntu instruction followed by the run apt-get update. apt-get is a package manager which enables us to install all kinds of software. The apt-get update command we just added to our Docker file will update apt-get so it knows what the most up-to-date version is of all the different software it can install for us. Using another run instruction on the following line, we download Python using run apt-get install python 3. Like you can see at the bottom of the slide, some bash commands require user input. While a Docker image is building, it is not possible to manually give any input to the bash commands Docker runs. Instead, we can pass the -y flag to apt-get install to make sure it doesn't need any input. Once we add run instructions to our Docker files, we'll notice that building a Docker file can take seconds to sometimes tens of minutes, because Docker is actually running the commands specified with run. For example, building a Docker file with from Ubuntu and run apt-get update will take the same time as us running apt-get update on Ubuntu, which is 2 seconds for the example on the slide. Here is a summary of the new commands and instructions you can refer back to when completing the exercises. We've seen the basics of building images. Now, we'll learn how to add files to our images. The run instruction allowed us to execute bash commands to create an image, but we can't use it to move files from our local file system onto the image we're building. To copy local files to our image, we use the copy instruction. The copy instruction needs 2 parameters. First, we pass to it the path of the file we want to copy, including the name of the file we want to copy. The second parameter is the destination path inside the image. We can choose whether to end the destination path with a file name. If we do not pass a file name, the file will get its original name. If we don't specify a file name in the source path, then instead of just a single file, the entire contents of the folder will be copied, including subfolders. For example, if we have a folder called pipeline_v3 with 2 files and a subfolder with 1 file, we can copy both files and the subfolder with its file using the copy instruction ending in pipeline v3/. It is not possible to copy files from a parent directory when building a Dockerfile. For example, let's say we're in the projects folder when we run docker build. A copy instruction in a Dockerfile that tries to copy the init.py file from the parent directory of the current directory into the image will fail with a not found message we can see on the slide. Another common way to include files in an image is to download them during the image build. While there is an instruction that allows us to do this, the add instruction, best practice is to use several run instructions and bash commands to download and unzip files. First, use curl to download a file to a local directory. Then, unzip it using the unzip command if it's an archive. Finally, once we don't need the zip file anymore, we can remove it with the rm command. Any instruction in a Dockerfile that downloads files will add to the size of the image, even if the files are removed in a later instruction. To ensure images don't become unnecessarily big, we should download, unzip, and remove the original file in a single run instruction. This can be done by chaining the commands using a backslash and $ampersand. The backslash makes it so bash commands can span multiple lines, allowing us to keep our Dockerfile readable. The $ampersand tells the shell to execute the commands one after the other. Combining them allows us to create a single run instruction that is still easy to read over multiple lines. By using this best practice on downloading and unpacking archives, we ensure our image is as small as possible, making it easier to share and faster to run. Here is a summary of the new commands and instructions you can refer back to when completing the exercises. Up to this point, the images we created don't run anything by default. Now, we'll see how to add a default start command to our images, and how to override the start command when we start an image. When we start a container from the Hello World image, the container will start, print text, and then stop. The creators of this image chose a start command that prints text and then exits. This makes sense in the context of a Hello World image. It wouldn't make sense for the creators of an image with the goal of running Python to do the same. Instead, it would be useful for their image to start a Python session for the user automatically and also to exit the session once that Python session is stopped. Docker images have this flexibility. Using the cmd instruction, we can choose any shell command to execute when a container is started from the image. Like everything else we add to images, we can add a start command using an instruction in a Dockerfile. This instruction is cmd. Cmd accepts a single parameter, the shell command to run when the image starts. The shell command runs when somebody starts a container. It is not executed when using docker build to create an image from the Dockerfile. Adding a cmd instruction to a Dockerfile does not increase the image size and does not add any time to the build. If multiple cmd instructions exist in a single Dockerfile, then only the last one will have any effect. When building an image for a specific use, it makes sense to set the cmd instruction to start an application related to this particular use. This could be starting a Python-based data analysis or starting software like a database that accepts outside connections. Another typical pattern is to run a script at startup that starts multiple other applications. With the cmd instruction, we set a shell command to run when a container is started from the image. The container will stay running until the shell command exits. The Hello World image only prints text and exits right after doing so. An image that starts a database, by default, will stop if the database is stopped or crashes. The more general the use case of the image, the more flexible the start command should be. For example, if we make a general usage Ubuntu image, simply opening a shell would make sense as a start command. The image will then exit when the user exits the shell. While the cmd instruction sets a default start command for the image, this default start command can be overridden when starting an image using the docker run command. Just like we pause the image we want to start to docker run, we can pass a second optional argument which will override the cmd instruction set in the image. Often, when replacing the start command of an image, we will run the image in interactive mode using the -it flag. Using a shell as a new start command, for example bash, allows us to look around the image, discover files, and see what's installed. Here is a summary of the new commands and instructions you can refer back to when completing the exercises. Building Dockerfiles can take some time. However, building the same Dockerfile a second time is much faster. Let's get some insight into why and when this is the case. When learning about the run instruction, we saw that building images can take significant time because the shell commands are actually run when the image is built. This is necessary because what is saved in the resulting image is not the instructions in the Dockerfile, but the changes in the file system the instructions make during the build. For example, if you have a run instruction with a shell command that downloads and opens a zip file with several files inside, the resulting image will contain those files. During the build, an image keeps track of which instructions in our Dockerfile created which change to the file system. We can view an image as a list of consecutive changes to the file system, with every entry in the list corresponding to a specific Docker instruction in the Dockerfile. Together, all the changes to the file system for a single instruction in the Dockerfile are called a layer of the image. All layers together make up a Docker image. There is also some metadata, like the start command set with the cmd instruction. While building a Dockerfile, we can clearly see when Docker is working on the next layer and on which layer it is working from the output. Like at the bottom of the slide, Docker will print which step it is building out of the total amount of steps whenever the next instruction in a Dockerfile starts building. When building a Dockerfile that we have built before, in front of each layer being built, it says cached in capital letters. Docker detects which Dockerfile instructions have not changed, and instead of rerunning the Dockerfile instruction, it uses the known result it has stored. Docker will only use cached layers to speed up our builds if the Dockerfile instruction is exactly the same and all previous Dockerfile instructions are also identical to when it originally created and stored this layer. Understanding when Docker layers are cached when building images is important for two reasons. First, it will help us understand why sometimes our image stays the same even though we change and rebuild it. For example, if we have a run apt-get update and apt-get install Python 3 instruction in our Dockerfile, and a new version of Python 3 is released, rebuilding our Dockerfile will not change anything in the resulting image. Docker will see the same instructions as when it last built this Dockerfile and will assume that the result is the same. It cannot know that rerunning apt-get update will give another result. Understanding when Docker layers are cached is also important because it will help us write Dockerfiles which we can make changes to without all layers having to be rebuilt. This can be done by ordering the instructions in the Dockerfile from least changing to most changing. This is why we always want to put the Dockerfile instructions to install packages before instructions to copy files into the image. Often, we'll change the files when improving our work or fixing bugs, but the packages we need rarely change. This ensures as many cached layers as possible can be reused. Let's look at a new type of interaction between Dockerfile instructions. The from, run, and copy instructions only affect the file system, not each other. If we copy a start.sh file from our local file system into an image, we can then use the run instruction to execute this file. The two instructions didn't change each other's behavior directly, but both used and changed the file system. However, some instructions can influence other instructions directly. The workdir instruction changes the working directory instructions are executed in, and the user instruction changes which user is executing the following instructions. When using a Dockerfile instruction where we have to specify a path, we can always use a full path. For example, a path that starts at the root of the file system, like in the first example on the slide. When working with long paths, this can quickly become hard to read. The alternative to using full paths is the workdir instruction, which allows us to change the directory inside the image from which all subsequent instructions will be executed. For the copy instruction, we change the current path on which relative paths will be based. Like with the copy instruction, other Dockerfile instructions are influenced when the working directory is changed with workdir. This includes the run and cmd instructions. The effect on the run instruction is straightforward. The shell commands executed by the run instruction will be run in a directory set by workdir. This allows us to make the run instructions more readable and removes any unclarity about where the files we are running are located. The workdir instruction also changes the working directory in which the shell command of the cmd instruction is run. If a user of the image overrides the cmd, their replacement start command will also be run in the path set with workdir. What you can do in a Linux operating system or OS depends on your permissions. Your permissions, in turn, are set by assigning you a user. For example, a data science user could be allowed to access the datasets folder while other users are not. There is a unique user called the root user, which has all permissions on the system. Best practice is to use the root user to create one or more new users and only give these users the permissions required for specific tasks. Then, we should stop using the root user and use these better scoped users instead. When writing Dockerfiles, we should follow this best practice and not run everything as root. The image we start our Dockerfile from will determine the user. For example, the Ubuntu image uses the root user by default. Any run instructions we put in a Dockerfile starting from Ubuntu will be run as root. This has the advantage that all folders are accessible and we won't get errors about permissions when installing anything. However, it is unsafe as all instructions will run with full permissions. The user Dockerfile instruction allows us to change the user in the image. Any following instructions will be run as the user set by the user instruction. It can be used multiple times, and the latest instruction will determine the user executing the following instructions. The user instruction changes the user with which the following instructions in the image are run. The last user instruction in a Dockerfile will also control the user in any containers started from the image of this Dockerfile. Here are the two new instructions for you to refer back to when completing the exercises. Using variables in our Dockerfiles allows us to make them less verbose, safer to change, and easier to update. Let's see how that's done. First, we will look at the arc instruction. The arc instruction allows us to set variables inside a Dockerfile and then use that variable throughout the Dockerfile. It is followed by a space, then the name of the variable we want to create, an equal sign, and the value of the variable. Later commands can then reference this variable using a $sign followed by the variable name. However, it can only be used in the Dockerfile. The variable won't be accessible after the image is built. In other words, if you define a variable with arc in a Dockerfile, build an image from that Dockerfile, and then start a container from that image, that variable will not exist inside the container. Typical use cases for the arc instruction are to define a version we need in multiple places throughout the Dockerfile. Like in the first example on the slide, we specify a version of Python called Bionic compiled for Ubuntu. Defining a path to a project or user directory is also helpful as an arc. This allows us to make any instructions using this path less verbose and makes it more apparent at a glance that all files are going to the same folder. The arc instruction can also be set in the Docker build command, giving us even more flexibility. At the top of the slide, you see the same example Dockerfiles as on the previous slide. By using the build-arc flag when running docker build, we can set another value for the project folder variable, which overrides the original value during that build. The second way to define variables in Dockerfiles is by using the env instruction. The syntax is identical to the arc instruction, but unlike the arc instruction, variables set with env are still accessible after the image is built. While variables set with arc are used to change the behavior of Dockerfiles during the build, variables set with env are used to change behavior at runtime. Typical use cases are setting variables used by applications when they are starting, like database directories or users, or setting an application to production or development mode. Unlike arg variables, it is not possible to override env variables at build time. However, it is possible to override env variables when starting a container from an image. This can be done using the -env parameter of the Docker build command. For example, in the official Postgres image, there are several env variables available to configure the container. Both env and arg variables seem convenient for adding passwords or other secrets to a Docker image at build or runtime. However, both are not secure to use for secrets. Anyone can look at the variables defined in a Dockerfile after the image is built with the Docker history command. This command shows all the steps that were done to build an image. If, instead, we pass variables at build or start time, they can be found in the bash history of the host or image. The bash history is a list of all shell commands executed by a user. Keep in mind that if we use secrets to create our image without using more advanced techniques to hide them, they will be shared with anybody we share the image with. Here is a summary of the new commands and instructions you can refer back to when completing the exercises. Containers don't make everything automatically secure. Let's look at what security containers give us inherently and where we still need to be vigilant. Docker inherently provides more security over running applications locally because there's an extra layer of isolation between the application and your operating system. This makes it much safer to open an application or archive from an unknown source in a container in comparison to doing the same on your local machine. However, that doesn't mean it is 100% safe to do so. A malicious payload can escape the container's isolation and infect the host. Attackers breaking out of a container to the host operating system is the main risk of using containers. Docker and other container providers spend extensive resources on making their containers as secure as possible. Additionally, there are several things we, the creators and users of images and containers, can do to make both more secure. The safety measures we'll be discussing next might seem like they won't do much if we're just sharing images with colleagues or using them to run workloads locally. However, a widespread use case for images is running them on remote machines and allowing external access. For example, to run a database or a pipeline in a production environment. It is in those scenarios that the following safety measures become critical. The first step to creating a secure image is choosing the right image to start from. Anybody on the internet can provide images for us to use or build on top of. However, using images from an untrusted source is a security risk. The official Docker Hub registry provides thousands of images and allows the filtering of trusted content in 3 different ways. All 3 trusted content filters will give us images we consider safe for most use cases. Even images downloaded from the official Docker Hub repository aren't always up to date. Applications release updates all the time, and even operating system updates aren't incorporated into images the minute of their release. In the slide, you can see the extremely popular Docker official images Ubuntu and MariaDB, which were updated 2 weeks and a month ago. While it could be the case no safety-related updates have been made to anything installed in these images since then, best practice is to update the software to its latest version in images ourselves. What's better than ensuring all software in our images is updated? Having less of it. There is no safer piece of software than one we haven't installed. When creating a secure image, ensure you only install the software you need for its current use case. This also means we'll have to keep less software up to date. All previous measures are of little use if we allow anybody who gets access to a container to install anything they want. The solution is not to leave the user in our images as root. Often it is needed to install and configure applications as root. After that, the user in our image should be changed to a user with fewer permissions. If, for example, we change the user before the CMD instruction that starts our pipeline, we ensure that any malicious code in the pipeline does not have root access in our container. Keeping these best practices in mind will put you on the right track to safely working with Docker.
Hi and welcome to the course. I'm Frank, your instructor in this introductory course about Kubernetes. Together we will have an exciting journey through the world of container orchestration. Before we dive into the subject, let me briefly introduce myself. I have many years of experience as a platform architect and have done a lot of projects in different industry sectors. I have been helping to implement software using Kubernetes since 2018, and I'm typically involved in projects using the software stacks and cloud providers shown on the lower right. So without further ado, let's get started. To understand the value and positioning of Kubernetes in today's software landscape, let us briefly revisit how software is designed today. Historically, software was developed as monolithic applications. These are large self-contained units ready to operate independently from other systems. While this approach has its merits, it also presents significant challenges. Monolithic software can be difficult to maintain and update, leading to prolonged release cycles. In contrast, modern software development has shifted towards a more modular approach, utilizing what is known as microservices. These are smaller, independent components that make up an application. This architecture greatly simplifies maintenance and updates, resulting in shorter release cycles and the ability to deploy new features more rapidly. Additionally, this modular design is exceptionally well suited for cloud computing environments. Nowadays, modern applications consist of tens, hundreds, if not thousands of these building blocks. This introduces a crucial question. How do we deploy, maintain, and update them? The answer is, of course, via containers. Each component is deployed or delivered in its own container, which includes all the prerequisites needed to run that component. However, another challenge emerges. How do we manage all these containers, ensure they operate correctly, and keep their versions up to date? This is precisely the role Kubernetes plays. Kubernetes is what we call these days cloud native. Let us look into this in more detail. Cloud native is a way to build, deploy, and manage software in cloud environments. Clouds provide infrastructure like virtual machines for computing, networks to connect these machines, and of course storage that all machines can access concurrently. All of this infrastructure can be scaled, which means that we can lease more or less of each component independently of each other. For example, if we currently use 3 virtual machines to run our application, we can add 2 more machines and use them immediately. We can also purchase more storage for our application without increasing the number of virtual machines. Now, a cloud-native application has been designed to use the scalable infrastructure efficiently. One way to achieve this is using containerization and Kubernetes. Kubernetes is cloud-native, which makes deploying and managing our application very simple. It also enables easy scaling of applications. Kubernetes is an open source project invented by Google. Everyone can download and use it. However, installing a functional Kubernetes may not be easy, as it involves a lot of knowledge about distributed computing. While it is not easy to install, almost all cloud providers offer Kubernetes as a managed service, which we can use easily. By the way, Kubernetes is often abbreviated as K8S. After the recap about modern software design, let us dig deeper into the relationship between Docker and Kubernetes. Remember, these days, typical software stacks consist of many individual containers. Numbers can reach up to tens, hundreds, sometimes thousands of individual containers. Now, managing all these containers is known as container orchestration. Nowadays, we can choose from many container orchestration tools like Docker Compose, Docker Swarm, Apache Mesos, HashiCorp's Nomad, and of course Kubernetes. Kubernetes has gained a lot of popularity in recent years, and it dominates the market right now. There are many reasons for this, and we will learn about this in a second, but let us mention a primary reason right now. Kubernetes is available for all important environments. You can use it in any cloud, but also on-prem or even in hybrid scenarios. That makes it an excellent solution for deploying your software. So why has Kubernetes gained so much popularity? Well, it makes solving the typical challenges of container orchestration relatively easy. These challenges are when to deploy your containers and on which physical hardware, how to enable networking for container communication, what to do when a container stops working, how to make sure that your containers are started and stopped in the right order, or how to attach storage. To solve all these challenges, Kubernetes interacts with so-called container engines that live on each computer you want to run your containers on. Kubernetes tells the container engines to start or stop your containers in the correct order and in the right place. You will learn a lot more about this architecture in the next lesson. Docker is indeed the container engine of choice in many cases. Kubernetes interacts with Docker as the container engine and will instruct it to start or stop your containers. We typically use Docker to create and update Docker images and to create containers from these images. Kubernetes will never create Docker images for you. That is the job of Docker. Kubernetes is an application on top of Docker that orchestrates all your containers. Before getting deeper into the architecture of Kubernetes, let's get a little more interactive with the next exercise. To prepare that, let's talk about how we interact with Kubernetes, especially how we use the command line tool kubectl, or how we like to pronounce it, kubectl. One way to define the containers we want to run on Kubernetes are manifests. These are YAML files which describe the containers you want, how to configure them, where they should run, and a lot more. On the left, you can see an example of such a manifest. Don't worry, we will get into the details later. These manifests are declarative, which means you describe what you want, or in other words, the state you want to achieve. They are not imperative. You do not describe how to achieve that state. We will learn a lot more about the architecture of Kubernetes later on, but let us introduce kubectl already here. Kubectl is a command line tool to interact with Kubernetes that comes with many commands and options. It reaches out to the Kubernetes API, sends our manifests to Kubernetes, and Kubernetes will then compute what to do in order to achieve the state we want. Having explored Kubernetes' value, let's dive into the core components of its architecture. Kubernetes is built from many elements. Let's cover the most important ones. The largest entity in the Kubernetes world are so-called clusters with their control planes. Clusters are built from nodes, and pods run on nodes. We will also cover services, which are used to establish network connectivity. A Kubernetes cluster consists of network-connected computers known as nodes. These nodes can range from servers in a data center or virtual machines to simpler devices like laptops or even Raspberry Pis. Each node is equipped with CPUs, memory, local storage, and potentially specialized hardware like GPUs. In the Kubernetes world, we install a so-called control plane somewhere in our cluster. We will not get into the details of this control plane, but remember, the control plane manages our nodes. It makes sure that they fulfill the requirements to participate in our cluster. Kubernetes clusters are scalable, ranging from small setups of 1 to 3 nodes to extensive networks of hundreds or even thousands of nodes. The nodes of our cluster typically run some version of Linux and a container engine. Nodes are also called worker machines. They run the containers we want to schedule. Nodes run the so-called Kubernetes kubelet. This agent lets our containers run in so-called pods, and we will learn about these next. By the way, we can add or remove nodes from and to our Kubernetes cluster at any point in time without any downtimes. Cool. Now let's talk about pods. A pod is the smallest computing unit we can deploy in Kubernetes. A pod is a set of one or more containers, for example, Docker containers. The containers of a pod belong together, and for that reason, they are always deployed together. They share local storage and network. Remember, by design, pods are what we call ephemeral. That means they live only for a relatively short time, and they can and will be terminated and recreated on other nodes at any point in time. The pod's ephemeral nature, being terminated and recreated frequently, might seem counterintuitive regarding stability. However, this design grants Kubernetes the flexibility to manage incidents efficiently, enhancing overall application reliability. Lastly, let's talk about Kubernetes services. A service is a resource to expose network connectivity. When we want to connect to our pod, or when we want to establish communication between pods, we need to deploy such a service. The reason for this comes from the ephemeral nature of the pods. Each pod has its own unique IP address, which changes anytime our pod gets redeployed. Now, services are not ephemeral. They offer stable connectivity. In the picture on the left, 2 services have been deployed. Service number 1 has connected all the gray pods to it, so whenever we call that service, one of the gray pods will respond. Service number 2 is connected to the purple pods, so calling that service gives us a response from one of these 3 pods. Now, here's just a short cheat sheet for what we have discussed. Welcome back. Now we will learn how to deploy stateless applications using Kubernetes. Before doing so, we will learn more about kubectl and manifests. As we already know, kubectl is the main tool for interacting with Kubernetes. Here are the important kubectl commands we will use. We can create and change objects, such as pods or services in Kubernetes, using create and apply, using the command line option -f, which is short for file. We can see a summary of objects by using the get command. Detailed information is available via the command describe. Kubectl is also a great tool for monitoring the state of Kubernetes. It comes with extensive help, which is available via the command line switch --help. Manifests are declarations that come in YAML or in JSON format. On the left-hand side, we can see an example of a YAML manifest. There are 2 important sections: metadata with essential meta information and spec to declare object specifications. These sections can be quite deep, depending on what is being declared. The manifest shown here is complete and fully working. It would create 5 replicas of Nginx, a well-known web server. Let us explore how we deploy our first application in Kubernetes, specifically a stateless application. Stateless applications are a general concept and not specific to Kubernetes, but they fit ideally into Kubernetes architecture. Stateless applications do not save any internal state or context of processed data. This means that they don't remember any previous activity or data they've handled. If such an application gets interrupted or stopped, a new replica is created and can start working immediately. To give an example, consider an application that queries a database. Each new query is unrelated to the previous query, so no context or history is needed. In Kubernetes, stateless applications can be realized easily with Kubernetes deployments. Here you can see a sample manifest for such a deployment. Let us go through the individual sections of this manifest. API version defines the Kubernetes API and version to be used. For deployments, we use apps/v1. Kind indicates that we will create a Kubernetes deployment. The metadata section defines various meta information we will cover later in this course. The spec section defines the detailed specification of our deployment. For example, replicas defines the number of replicated pods the deployment should consist of. Selector is used to define how pods will be managed. Kubernetes will use the selector rule to find individual pods for applying changes. We will learn more about that later in the course. Finally, template defines how new pods are created. If Kubernetes decides to create a new pod for the deployment, it uses the defined template to add labels, create containers with respective name, Docker image, and other details like network ports for communication. We use kubectl to apply the manifest to the cluster. The command kubectl apply -manifest.yaml will send the manifest to Kubernetes. The control plane will decide on which node to schedule the pods, and the creation of our pods is triggered. Pods in a deployment get a unique but random identifier. In that sense, pods are treated as completely equal. Each one is as good as any other. In this video, we will learn how to scale and monitor stateless applications using Kubernetes. Let's dive in. Scaling means to add or remove resources. Adding resources is called scaling up, and removing them is called scaling down. We scale up to react to more demand, for example, due to increasing load on our application or because more storage is needed. We scale down to save on resources, for example, when load on our application goes back to normal. Now, how do we scale the number of pods in Kubernetes? This is very easy. Either we change the number of replicas in the manifest and reapply it, or we use the command kubectl scale deployment with the command line argument --replicas. To be clear, applications need to be designed for scalability in the first place. In fact, many legacy applications, or in particular monoliths, are typically not scalable in the way shown here. We cannot just add pods to a monolith and expect such an application to handle the load better. That is why we recapped software design previously. We need modern and cloud-native applications for scalability. These applications have to be designed accordingly so that they can be scaled with ease. Monitoring is a crucial real-time process for observing applications. Monitoring enables us to react to all kinds of problems and challenges like outages, load spikes, or storage that may be exhausted. There are many modern monitoring applications for Kubernetes. Examples include Prometheus and Grafana, but several other open source and proprietary solutions exist. Here, we will use kubectl to perform basic monitoring tasks. Specifically, we will use the command kubectl get, followed by the objects we want to monitor. In the first example, we use kubectl get pods to observe all pods and their current status. In the second example, we use kubectl get services to monitor all our services. In this video, we will learn how to deploy, scale, and monitor stateful applications using Kubernetes. We will stress the similarities and differences compared with deploying stateless applications. Let us briefly recap what we have learned about stateless applications. Such applications are mapped to deployments, and each pod of the application does exactly the same tasks. Each pod is an exact replica of the others. Stateful applications, on the other hand, need pods that are not exact replicas of each other, as each pod may work on different tasks. As we will see, much of what we've learned so far can be applied in this chapter as well. Stateful apps are a general concept and again fit well to Kubernetes. Stateful applications save some internal state. When interrupted or stopped, a new pod is replicated and can continue to operate from the saved state. We use stateful applications all the time. For example, database backends like PostgreSQL are stateful. Each time we update data using any of the pods, the new data needs to be persisted. Now, when a pod terminates for whatever reason, a new one is created and this pod needs to pick up the saved state. In Kubernetes, there are so-called stateful sets, which are used to create stateful applications. Here is a sample manifest for such a stateful set. A stateful set has the same sections that we know already. API version, kind for declaring a stateful set, metadata, and spec for declaring detailed specifications of our stateful set, like the template for our pods and the number of replicas. Again, we also have a selector section, which we will discuss later. We deploy stateful sets like we deploy deployments by executing the command kubectl apply -f manifest.yaml. However, stateful sets are created a little differently compared to Kubernetes deployments. Pods are created in order, not all at once like the pods in a deployment. Furthermore, pods get predictable names like pod-0, pod-1, pod-2, and so on. This ensures that pods of a stateful set have an identity, in contrast to those of a deployment. Hence, with this identity, different pods of a stateful set can perform different roles. Stateful sets can also be scaled up or scaled down. Again, this is extremely easy. We either change the number of replicas in the manifest and reapply, or we use the command kubectl scale stateful sets. When we scale up, additional pods will be created one after another. For example, if our existing pods are pod-0, pod-1, pod-2, then first pod-3, then pod-4 will be added to the set. When scaling down, the pods created last will be deleted first. For example, from our sets of pods, pod-4, then pod-3 will be removed first. For monitoring, we have the same workflows like before with deployments. Monitoring lets us react to problems like outages, load spikes, or missing storage. Again, we will use the command kubectl for basic monitoring tasks. Commands are the same as with deployments. For example, we can use kubectl get pods to get all the pods in a stateful set with their current status, or we can use kubectl get services to get all the services that a stateful set may use. So far, our pods have been ephemeral, meaning we lose any data once the pod is terminated or recreated. However, ensuring data persistence across pod restarts is often a key challenge. Let's explore how Kubernetes addresses this. The fundamental objects for storage in Kubernetes are persistent volumes, or PVs for short. We create and maintain PVs in parallel to other objects like pods and have them act as simple blocks for storage. We map or assign these PVs to pods using persistent volume claims, or PVCs. When mapped to a pod, we can use the PV for any data that needs to survive when the pod is terminated or restarted. Therefore, PVs give us one of the most important features of cloud-native software design: the separation of storage and compute. Storage, our PVs, are separated from our pods, which do the compute and use data stored on the PVs. We have two ways to create or provision PVs. The first way is to create them manually. This is done by a Kubernetes admin and not by users like us. The second way is to provision PVs dynamically, and we, as regular Kubernetes users, can do this ourselves. We provision PVs dynamically using so-called storage classes, or SCs for short. SCs are designed to provision persistent volumes without any human intervention. They define basic properties of the PVs to be dynamically provisioned. This ensures that PVCs can be automatically matched with appropriate PVs based on storage needs. And hence this type of storage provisioning is a key enabler for automation. Now, storage classes are objects we simply use. These are created and maintained by our friendly Kubernetes admin, which means they are ready to be used by us. Further, real-world Kubernetes in general provides many types of storage. Typically, these types are defined by different criteria like availability, latency, cost, or applied backup strategy. All in all, dynamic provisioning of PVs using storage classes is now standard in Kubernetes. If we are unsure what to do, we use storage classes. Keep in mind that only 3 Kubernetes objects are involved in storage: persistent volume claim, and storage class. When we declare a pod that has demand for persistent storage, first we create a persistent volume claim. This PVC has Kubernetes create a persistent volume dynamically for us. Second, this persistent volume is mapped automatically to our pod. Our choice of storage class defines details like the availability and backup strategy of our persistent volume. Most importantly, this persistent volume survives, even when the claiming pod is terminated or restarted. When restarted, The same existing PV will be bound to the pod again, and hence no data is lost. Let us dissect some manifest snippets. First, we see the declaration of a pod. We declare demand for storage with a volume mount named pv-mydata and a path named /mydata. In the volume section, more details are given. The volume named pv-mydata will be created and bound using the persistent volume claim DataCamp-pvc. Second, we see the declaration of the respective persistent volume claim with the name DataCamp-pvc. The storage class standard is chosen here. Further, we define the access mode, which in our case is read-write-once. Finally, choosing the standard storage class and a 5 GB volume size in the PVC definition is based on the typical needs of our application, balancing performance and cost. As you have already expected, kubectl offers a complete set of commands to deal with storage. For example, kubectl get_sc will list all available storage classes, and kubectl get_pvc shows all deployed persistent volume claims. Further, kubectl get_pv lists all deployed persistent volumes. Plus, as usual, kubectl apply-f manifest is used to deploy the storage resources which have been declared in respective manifests. Let's dive deeper into networking, load balancing, and security in Kubernetes. Let's look at Kubernetes labels and selectors in more detail. Labels are key value pairs that can be attached to objects like pods, persistent volumes, or even nodes. We use labels to organize subsets of our objects, and we can modify our labels at any time. For example, we could attach the label value pair environment equals prod to some of our pods, or we could attach a label has_GPU with the value true to the nodes in our cluster that have a GPU. We use selectors to identify objects using these labels. For example, we could use the has_GPU label to schedule a pod that needs the compute power of a GPU on a respective Kubernetes node. Let's recap services and dig a little deeper into networking. As we have learned previously, we use services in Kubernetes for networking. The reason is that each pod has its own unique IP address, which changes anytime our pod gets redeployed. Services are not ephemeral. They offer stable connectivity. Services can be created using manifests. On the right, we have a snippet of a service manifest, which would deploy the service named Kubernetes_service_2 as shown on the left. Besides metadata, which we declare as usual, our selector selects all pods that have a label named app with a value of app2. Now, if our purple pods on the right have this label attached, these pods would be assigned to our service, and we can use it to start communicating with other services. Load balancing is another feature that is correlated with networking and easy to implement in Kubernetes. A load balancer simply distributes network requests evenly over pods. This avoids uneven load, which leads to more efficiency and lower response times. In the example on the left, the Kubernetes Service 2 is a load balancer and has 3 pods attached. Requests for the service will be spread out to the 3 pods. Load balancers are just a special type of service which we can declare in the spec section of the manifest. When we deploy the service, our Kubernetes provider will create a load balancer for us. We do not need to declare additional manifests to deploy actual load balancer software. Let's finish networking with a few words on ingress. Ingress allows us to route HTTP and HTTPS traffic to services. This is done by rules that define which service is used by which requests. In our example, the ingress rules route requests for endpoint /for_service_1 to Kubernetes service 1 and requests for endpoint /for_service_2 to Kubernetes service 2. The respective pods finally serve these requests. Finally, let's talk about security in Kubernetes. Security is an essential field, and modern IT architecture has to implement many security standards and best practices. but it is also a very complex field, and we cannot cover all the details here. However, we should keep in mind that Kubernetes comes with all the necessary components to run our applications securely. For example, we have the Secrets API that allows to store confidential objects like passwords, tokens, keys, and others. Furthermore, there is tooling to enable encrypted network communication. Plus, there are methods to authenticate users, allowing modern role-based and attribute-based access control for our users. Kubernetes can also be used to create and maintain data pipelines. Let's discuss how. First of all, what are data pipelines? In a most general form, a data pipeline is a set of processes to move data from a source to a destination, transform data from one form into another, and analyze the data to get insights from it. Most data pipelines consist of three major steps: extract, transform, and load, or ETL. What does this mean? Let's first describe a so-called ETL pipeline. The extract step simply copies data from a source system, like a database, a file system, or an object store. After extraction, the data from various sources is transformed into a meaningful schema. This allows for easy analytics and helps keep track of what has already been extracted. After this transformation step, the data is loaded into a target data sink. In ETL, this is typically a data warehouse. In recent years, another type of data pipeline has gained popularity, and this is ELT. In ELT, extraction also takes place like in ETL, but then loading into a target data sink takes place immediately. This is typically a data lake. After loading takes place, data can be transformed into a meaningful schema when needed. The exchange of these last two steps allows data consumers like data scientists or data engineers to transform the loaded data as needed, and hence offers additional flexibility compared to ETL. ETL as well as ELT data pipelines map nicely to Kubernetes objects. Our extract, transform, and load steps can be deployed using deployments or stateful sets, and the data that gets extracted and transformed can be stored using persistent volumes. Further, if we use scalable solutions for all of these steps, we can use Kubernetes to scale our deployments and our storage where needed. For example, let's assume that we have deployed 5 pods to perform our transform step, as shown in the figure. If these 5 pods cannot deliver enough throughput to transform all of our extracted data in due time, we could scale up the number of pods to 6, 7, or more. The same is true for storage. As the amount of data increases in our pipeline, we can attach storage as needed and scale accordingly. Let us mention some typical open source tools and software that can be used for data pipelines in Kubernetes. First of all, for extracting from various source systems, we can use tools like Apache NiFi and Apache Kafka, in particular the Kafka Connect ecosystem. For transforming data, there is Apache Spark, again Apache Kafka, and databases that use SQL like PostgreSQL. For loading data into target data sinks, we can use Apache Spark, Apache Kafka, in particular KSQL, and PostgreSQL. For storage, we can deploy object stores like MinIO or block storage like Ceph. In our last video, let us understand how MLOps and Kubernetes can work together. First of all, what is MLOps? MLOps, or machine learning operations, is a paradigm to deploy and maintain ML models in production. It is a collection of best practice workflows with strong focus on continuous development and constant improvement of models. It is inspired by DevOps, which focuses on continuous development, deployment, and operation of software solutions. Similar to DevOps, ML models, as well as AI models or GenAI solutions, are developed and tested in isolated systems and then deployed to production. When productive, the models are continuously monitored, their accuracy is constantly measured, and improvements through retraining may be triggered. Data scientists, data engineers, and IT teams can work together on deployed models synchronously, hence ensuring their accuracy. Now, this paradigm of MLOps maps very well to Kubernetes. The isolated experimental systems that we need for development and testing can easily be realized by pods and Kubernetes storage, of course. We can monitor our productive ML models easily by following the lifecycle of our pods, together with the images we have deployed. We can also work synchronously as a team on model accuracy, as this is enabled from the very beginning by the architecture of Kubernetes. For MLOps on Kubernetes, several frameworks exist. The two best-known open source solutions are MLflow and Kubeflow. Let us have an overview of Kubeflow here. Kubeflow is dedicated to making the deployment of ML workflows on Kubernetes very simple. It covers each step of the ML model lifecycle. For example, data gathering, data wrangling, model training and testing, and deployment, of course. Kubeflow consists of several components which cover all of these steps. Most important, all these components work independently of each other. This enables maximum flexibility and lets us create all types of workflows easily. We can also use Python directly to develop and deploy ML models using Kubeflow. There is no need to use kubectl here. We can interact directly with the Kubernetes API. Let's wrap up what we have covered in this course. We started with an introduction to Kubernetes, and we have learned why Kubernetes is a very good framework to develop true cloud-native applications. After that, we discussed the architecture of Kubernetes with the control plane, nodes, pods, and services. Then we discussed storage and learned about persistent volumes, volume claims, and storage classes. We learned how to use kubectl, the command line interface to Kubernetes, and had a detailed look into Kubernetes manifests. We have seen how to deploy different types of applications using deployments and stateful sets. Additionally, we attached persistent storage to our applications, of course, the Kubernetes way. Finally, we applied all these concepts to data pipelines, and we have seen how Kubernetes can support ETL and ELT workflows. We also explained how Kubernetes supports MLOps, and we have deployed a simple MLOps workflow. There's a lot of where we can go from here. Security is one of the first subjects to dive deeper into. By learning more about service accounts, secrets, role-based access management, and more, we can deploy applications that are not only rock solid and scalable, but also comply with highest security standards. Next step could be Helm charts, and Kubernetes operators. These are advanced tools that help to deploy packaged applications and to maintain these in an easy way. Furthermore, advanced storage concepts are worth learning. Rook operators and Ceph allow for scalable storage concepts for any kind of application. CI/CD is another topic to explore. Kubernetes can be used for automated building and testing of software, and we can create the CI/CD pipelines we need. And last but not least, serverless applications is a subject worth diving into. Knative enables us to deploy serverless functions on Kubernetes, so we can use our resources extremely efficiently.
Welcome to the course covering the intermediate use of Docker. I'm Mike Metzger, a consultant in the data engineering space for over 10 years. This course will take your knowledge of Docker to the next level and help you utilize containers in your data career. Let's get started. As a quick refresher, let's review a bit about Docker. Docker is a container runtime, meaning it is a tool designed to run and manage various containerized applications. There are versions of Docker for all major operating systems, including Windows, Mac, and Linux. We can run containers using pre-built images or create our own images. Docker uses Dockerfiles, which are text files that act like instructions to create a new Docker image. Finally, remember that containers in Docker are instances of a given Docker image. Please note that this content is covered within DataCamp's introductory Docker course, which should be taken prior to this course. From our previous experience with Docker, we've used several commands, including docker run, docker stop, and docker build. We'll cover more about these commands and many others throughout this course. Before continuing, look at one of the most useful commands, docker-help. Docker-help provides a list of the available commands within the Docker toolset. For each of these commands, sometimes called subcommands, you can also run docker command --help to get further information about each individual command. For example, you can use docker run --help to get more specific information about the docker run command. Docker containers are typically created with the docker run command. In the default configuration, these containers will remain even after stopping or exiting. While this is the default behavior, there are situations where you'd like to run a container instance and remove it immediately upon exit. These situations can include development, testing, or running scripts. Docker provides an option to do this automatically using the docker run --rm command. For example, if you wanted to run a quick shell prompt in the latest version of Alpine and remove it automatically, you could use docker run --run alpine:\latest /bin/sh. Note that Alpine is a Linux distribution designed to take up very little space, like Ubuntu, but smaller, making it ideal for use with containers. We'll cover space optimization later, but you will see many different container images used in this course. The last /bin/sh is required on some containers to specify what program to run inside the container. In this case, we want to run a shell, which is /bin/sh. This command line option is referenced as cleanup or remove. A command we'll use extremely often is the docker ps command. We'll cover some of its capabilities in more depth here and later in this course. The docker ps command is used to determine the name, ID, running status, and other attributes of all the containers running with Docker on the local system. Not all this information is printed each time, so we can use the -a flag to see further information about existing containers. We will also cover other commands to get extremely detailed container information later on. Welcome back. Now we will look at how to share information between our containers and the host system. Let's get started. Let's consider a container instance's file system for a moment. Each container instance has its own file system, which is based on the image it was created with. Changes can be made to the file system, but are tied to that instance only. If we restart the container, the changes stay, but only for that specific instance. They do not apply to the other instances of that same container image. If we create a new container instance, it will not have those changes. You can see a quick example of this in the diagram. We have our original Docker image and create container 1 and container 2. Container 1 has a file in /home called new file. As this file was not created on container 2, it is not present there. Rather than modifying the contents of our running containers or always creating new Docker images, we can attach files or directories from the host system to a container. This allows for the persistence of data, whether log files, database files, configuration files, and so on, without the requirement of maintaining a specific container. We can use Docker to upgrade the container to a newer version, but safely keep all of our data separate. This technique, known as a bind mount, is one of a few options to share data between host and container. We'll discuss some other options later in this chapter. A bind mount can be read-only, where the container can see the data but cannot change it. The bind mount can also be read-write, but in this case, only one container can modify the contents at a time. Once attached, files or directories are not accessible to the host until the container using them is shut down. A bind mount is usually defined using the -v flag, specifically with -v source:\destination. The source is the file or directory on the host's file system to be shared, and the destination is the location within the container's file system where the source data will appear. Multiple -v commands are permitted per container. The maximum number varies, but generally you can add at least 16 bind mounts per container. In addition to the -v flag, there is a more verbose option, the --mount flag. We won't cover this here, but it tends to permit more specific options than are available with -v. One note is that a bind mount will hide any files or subdirectories that exist within the container. In other words, if we bind mount the /data directory to /home/mydata, anything present in /home/mydata in the container image is not accessible. Here are two examples of using bind mounts. The first is an Nginx web server container attaching the host's /html directory to the /var/www/html directory within the container. The second attaches the /pgdata directory and the pg.conf file on the host to the /opt/data directory and /etc/pg.conf file in the PostgreSQL container, respectively. Note that in all these examples, the local path must either start with a / or be a full path to the file. Welcome to Networking with Docker. Before discussing Docker's networking capabilities, we'll review its terms and concepts. Please note this video is not meant to be a true introduction to computer networking. A computer network consists of systems communicating via a defined method to share information. There are, among others, physical and logical networks. Common physical networks include wired Ethernet and Wi-Fi. Logical networking includes TCP/IP and application-level protocols like HTTP for web communication and SMTP for email. Networks are defined in various layers or levels. The combination of various components is referred to as a networking stack. Given the depth of information regarding computer networks, we will cover a set of terms you might encounter while working with Docker. The first term is host, a general term for a computer. A network is a group of hosts. An interface is a connection from a host to a network, such as Ethernet or Wi-Fi. Note that an interface can be virtual, meaning it's entirely in software. A LAN references a local area network, a set of computers at a given location. There is also the term VLAN, a virtual or software-based LAN. You've probably heard the term IP, or Internet Protocol, a method to connect between networks using IP addresses. There are two types of IP addresses in use today, the first being IPv4. IPv4 is currently in use and supports approximately 4.2 billion addresses, though many are reserved for special purposes. The address space is currently exhausted, meaning all addresses have been allocated. IPv6 is the newer version of IP and supports significantly more addresses and is still being deployed. TCP is the transmission control protocol and is used to reliably communicate between hosts on an IP network. UDP is the user datagram protocol and can communicate between hosts over IP where reliable communication is not required. Both TCP and UDP require a port value, a method to address different services on a given host via TCP or UDP. The port is a value between 0 and 65,535. Values below 1024 are typically reserved for privileged accounts like root. Values above 1024 are usually referred to as ephemeral or temporary ports. Another important concept is that application servers are said to listen on a given port. This means that it waits for new connections on that port and responds to clients from it. HTTP is an application protocol defaulting to TCP port 80 for web communication. There is also the secure version, HTTPS, running over port 443. SMTP is an email transfer protocol and uses TCP port 25. SNMP, a network management protocol, uses UDP port 161. Docker has extensive networking capabilities and can facilitate communications between containers and the host system. Depending on the settings, it can also allow communication with external hosts or the wider internet. Typically, communication is handled by exposing ports from containers to the host and acts like a translation between them. Containers can have their own IP addresses. You can use the command ifconfig or the command ip-adder-show to view the interfaces an IP is assigned. You can also add the interface name to see a specific interface. Look at the ifconfig example and the IPv4 and IPv6 addresses outlined in red. Note that the interfaces here are virtual between the host and the containers. Finally, you can use the ping command to verify connectivity. The -C flag requires a count for the number of pings and the host you wish to connect to, such as an IP address or a host name. Nice work on those last exercises. Let's take a look at another method to store data with Docker containers, persistent volumes. The first question is, of course, what is a volume? Volumes are another way to store data in Docker that is unrelated to the container image or the host file system. Docker manages volumes on its own using the command line tools. Technically, volumes can also be managed from the Docker API, but we won't cover the API in this course. One advantage of Docker volumes is that they can be shared with multiple containers. You still need to handle data access issues, such as two containers writing to the same file, but it is considerably more powerful than a bind mount option. It should be noted that volumes are higher performance than using bind mounts, and are recommended if there are performance concerns. Finally, Docker volumes exist until they are specifically removed, even if the container they're attached to is deleted. Volumes are managed using the Docker volume command and its various options and subcommands. To create a volume, we use the Docker volume create volume name. This defaults to creating a volume locally, but there are other options we'll discuss shortly. To view a list of existing volumes, we can use the Docker volume ls command. An alias, Docker volume list, works as well. There are some various filtering and formatting options available depending on our version of Docker. To see more extensive information about a volume, we can use the Docker volume inspect command. This command shows assorted metadata about the volume, including its name, mount point on the host or destination, and various options for the volume. Finally, we can also remove volumes using the Docker volume rm command. Let's look at a quick example of working with a volume. First, we'll create a volume called SQL data using the command docker volume create SQL data. This simply returns the name of the volume when it's created. Next, we can use the Docker volume ls to get a list of our volumes. You will likely see many volumes depending on the number of containers or volumes you've created. In this case, it shows the driver and the volume name. We'll discuss drivers in a moment. Let's also use the Docker volume inspect command, such as Docker volume inspect SQL data. This returns various metadata regarding the name, age, mount point, options, and so forth. To actually use our volume with a container, we use the -v command once again. This would look like docker run -v space volume name :destination path, and optionally :options. The volume name is the name of an existing Docker volume. The destination path is the location in the container where the volume is mounted. Options represent an optional comma-separated list of values to pass to the volume configuration. This can be something like the RO option for read-only. Note, there is also a -- mount flag with different options. We won't cover it in this course. For the last part of this video, we'll discuss the Docker volume drivers. Drivers are simply methods of storing Docker volumes. These can include various methods, but typically it's a local file system, which is the default. There are countless other drivers, but two very common ones are NFS or Unix file sharing. Another common option is using SMB or CIFS for Windows file sharing. Other drivers include options for remote systems, backup devices, and so forth. Welcome back. Let's look at how to make network services available from within Docker. As briefly mentioned, network services listen on a given port. As such, only one program can listen on a specific IP and port combo. For example, 10.1.2.3:80 would mean that a program on the host with IP 10.1.2.3 is listening on port 80. Consider what this would mean if we were trying to debug different web server versions that listen on that port. We could effectively only run one copy of the application given that only one program can listen on that IP port combo. We can partially solve our problem by wrapping an application in a container, meaning each container can now listen on the port. This is because the IP port combo is different for each container because each container has a different IP address. We can also now have multiple copies of a container running, including those of different versions running simultaneously. However, the question then becomes, how do we connect to the individual containers without knowing the specific IP addresses of each container? The answer to our problem is port mapping, sometimes called port forwarding or translation. Port mapping takes a connection to a given IP port combo and automatically forwards it to another IP port combo. In this instance, we can map an unused port or ports on our host and point it to port 80 on the containers. The Docker engine can handle this for us automatically with a command line option we'll mention in a moment. Let's look at a quick example with 3 containers running in our Docker engine. Each container is listening on port 80, which works as the individual containers have their own IP addresses. To make them accessible to the host or systems that can reach the host, we can use the port mapping to connect ports 5501, 5502, and 5503 to point to port 80 on the individual containers. To enable port mapping on a given container, we add a flag to the Docker run command, the -p flag. This is also known as the published flag. The -p flag requires 2 arguments written as the host port, and the container port. For example, to map port 5501 to port 80 in the container, we would use -p 5501:80. Also note that we can have multiple -p flags if there are different ports to publish from the container to the host. As a full command, we would run docker run -p 5501:80 nginx. This would set up the web server listening on port 80 in the container, and Docker would create the map from 5501 to 80 for us. Using Docker ps-a, we can look for the ports column to verify the mapping. In this case, the 0.0.0.0:5501 means any IP on the host with port 5501 should map to port 80 using TCP. The second part means the same thing, but for IPv6. Welcome back. We've just covered exposing ports manually in Docker, but let's cover exposing services via Dockerfiles. Our first topic for this video is the expose command within a Dockerfile. Expose technically defines which ports a container will use at runtime within the container. Each expose line should include a number for the port to use, a number /TCP or /UDP, such as expose 80 or expose 80/TCP. Note that a protocol defaults to TCP if we do not define a protocol manually. We can also have multiple expose entries per Dockerfile if multiple ports or protocols are required. It is important to note that this is primarily used as a documentation method, letting the Docker user know which ports should be exposed from within the container. That said, it does not actually expose the ports for use without defining a -uppercase-P or a -lowercase-p host port :container port command. The -uppercase-P flag will automatically map ephemeral ports to the exposed container ports. Remember that ephemeral in this case means high-numbered and unprivileged. The -lowercase-p flag works as described in the previous video and allows a specific port to be defined. Let's look at an example using the expose command. First, we've created our Dockerfile from the Python 3.11 slim image. We then add an entry point startup command. In this case, we're running Python's built-in web server. Finally, we add the expose 8000 entry to indicate that the container listens internally on TCP port 8000. Assuming our image builds correctly, we create an instance of the container using the docker run command. To determine the state of the container, we can use the docker ps-a command. Note that we've truncated the output slightly, but note the ports column. Here, the container is exposing TCP port 8000 as expected. Be aware, if we try to access this port from the host, it will not be reachable as we have not defined what host port to use. Now, we'd like to make the ports reachable from outside the container. The simplest method is to use the docker run -uppercase-P flag, which will automatically assign an ephemeral port from the host and map it to the internal container port. Note that this differs from the previous chapter, which uses a manual mapping with a -lowercase-p flag. We have a few options to see which port is used. The simplest is using the docker ps-a command as before. Note under the ports column that we now see a mapping, in this case 0.0.0.0:55001, pointing to 8000/TCP. This means if we make a connection with a web browser on the host at port 55001, it will automatically redirect to the container's listening port. Another more verbose method to find the exposed ports is the docker inspect command. If we run docker inspect container ID, we'll get a considerable amount of information in a JSON format. If we parse through the information, under the network settings :ports section, we'll see the exposed ports within the container and what host IP and port they are mapped to. Note that typically this information is overkill, but may be useful in cases of many exposed ports or more extended troubleshooting situations. Let's talk about creating networks within Docker and some of the capabilities we gain when doing so. Docker has extensive networking options, allowing the use of containers in many different situations. We will only cover a few options, but Docker can create networks to communicate between containers, the host, and external systems. Let's review several of the commands you'll be working with. Docker supports different types of networks using various drivers. The bridge driver is the default driver and allows communication to the internet, to exposed ports, and between containers on the bridge, but not further. The host driver allows full communication between the host and any running containers. This works for specific circumstances, but also has some security implications. The last driver we'll cover is the none driver, which completely isolates the container from communicating with anything else. It's helpful in testing untrusted containers and applications without concern for what they're doing. Many other types of drivers are available, and you can create your own if needed. We will primarily use the bridge driver when working with our networks. Our primary method for working with Docker networks is the appropriately named Docker network command. The Docker network actually takes subcommands in the form of a Docker network command to accomplish specific tasks. As with other Docker entries, you can use --help to gain further information about available options. There are several Docker network commands we'll use. We'll cover 3 here and others in a few moments. The first command is docker network ls, which provides a list of all Docker networks defined on the host. Docker network create requires a name argument, but can also take several other options, including the -d for the driver to use and various other details. Finally, we can use docker network rm network name to remove a given network. We can create a network named mynetwork using the docker network create mynetwork command. It will return an ID, the internal identifier Docker assigns to the network. Your system will return a different entry. If we run the command docker network ls, we can get a list of the network IDs and the information. Note that the IDs are a shorter form than what gets returned by the docker network create command. This is normal and expected. You may wonder how to connect a container to a given network. There are 2 methods available depending on your needs. The first is using docker run with a new flag, --network, and the network name. For example, we can create a container with the docker run --network mynetwork ubuntu bash. We can also connect a container later using the docker network connect network name container ID command. The container ID can be a literal container ID or the name given to the container. We have an example of docker network connect mynetwork ubuntu b to connect the ubuntu b container to my network. To check the details of the network, we use another command, docker network inspect network name. This provides configuration details, including the IP ranges assigned to the network. You can also see the actual IP addresses assigned to the containers. As an example, we can use the docker network inspect mynetwork command. This is an abbreviated output, but you can see the type of network driver and the various details. We can specifically see the IP address assigned to the containers connected to the network as well. Welcome back. We're now going to look at some options to optimize our container images. Let's get started. As you may remember, Docker images are the base of a given container. It is, in effect, the file system of a container and holds all content initially available to a container instance. Given Docker containers' relative power and flexibility, new users are tempted to add all potentially needed components to an image. While doable, this usually isn't recommended for several reasons. The first is the container image size becomes large and unwieldy, especially if you need to run multiple copies of the container image. It is also challenging to handle any security issues or required updates as there are many more dependencies between components. Finally, it's harder to combine containers without wasting space or bandwidth due to the large size. The usual recommendation when working with containers is to split the containers to the smallest level needed for a given task. We'll discuss this with an example in a moment, but it becomes much easier to combine multiple containers later versus building a single large image. This is like building with a reusable set of components instead of building fully from scratch each time. In this case, updates to specific software in our image only affect containers using that image, rather than all containers needing to do the update. We can also optimize the amount of space used, allowing for more efficient use and distribution of said container images. Let's consider a data engineering project that uses the following software. We need a PostgreSQL database, some custom Python ETL software, and our web server components. Now we could add all of these components to a single image, but we'd need to update this image anytime we needed to update the individual components, such as the ETL or web server setup. Also, let's consider how we would add a separate web server instance if, for example, our business wanted to provide a different level of access to a business partner. In other words, we'd have to set up a much more complex configuration within the container to handle both web server instances. Fortunately, Docker handles these issues well if we're willing to redesign our setup slightly. The main option is to split each software we're using into its own container image. In this case, we'd have a PostgreSQL image, an image for the ETL components, and a web server image. We could then create containers using these images as needed. We can build an optimized configuration for our use and can add or remove components as needed without affecting the rest of the configuration. If we needed to add a web server, as mentioned before, we only need to create a new web server container, not update our image and update each container in turn. You may be wondering how to determine the actual size of the images we're using. The simplest method is using the Docker images command. This will provide a list of images in use on the local system, along with individual image details, including the size of the image. Note that there are other options available for the Docker images command that you may use. Docker images --help shows further detail. Welcome back. Let's look at a fairly technical topic, examining layers in Docker. Docker images are made up of layers, which generally reference a change or a command within a given Docker file. Docker will automatically determine which layers can be cached or reused in other Docker images. For example, any image using the request library with pip could reuse this layer. A command's order and specific nature within the Dockerfile can affect whether layers are reused. You may wonder why we care about reusing layers. There are two primary reasons: faster build times and builds taking up less space. How can we determine the layers that exist within an image? We can do this using the Docker image inspect with the image ID or the name of the image. This command provides considerable information about the image, including configuration details, the system architecture it's designed for, OS details, and so forth. For our purposes, it also contains a rootfs layers section that provides information about which layers make up the specific image. As an example, let's look at the layers found in a Postgres Docker image. Note that Postgres is a database server, but you do not need any knowledge of it for this course. We'll use the command docker image inspect postgres:/latest. Under the rootfs section, we can see the list of layers included. The list of layers references the ID assigned to the layer. We won't inspect these further, but it is an interesting tool to see how layers are used within an image. It can sometimes be challenging to analyze the results of a Docker command, such as Docker image inspect. The JQ command line tool is used to read JSON data, like what is returned from the Docker image inspect command. In addition to parsing the JSON data, we can also use the JQ command to query specific portions of JSON data. Let's look at a couple of examples. Let's consider using JQ to look at a specific portion of the dataset, such as the rootfs data detailing the layers used in a Docker image. To use JQ, it's easiest to pipe the output of one command, in this case Docker image inspect ID of container, into JQ. After JQ, we enter the portion of the output we want in single quotes. First, we ask for open bracket 0 close bracket. This represents the first instance of data found in the JSON data. We then add another pipe symbol and the text .rootfs, representing the rootfs section of the JSON output. This content will likely be confusing until you've used it more. Treat everything after the JQ command as the recipe of what you want JQ to do. This outputs all of the information specified for the rootfs as previously. A second example is more complex, where we use JQ to count the number of layers present in an image. In this case, our initial command is the same as before, but the recipe fed to JQ is different. The open bracket 0 close bracket is the same, but it's piped to layer count : .rootfs .layers pipe symbol length. This tells JQ to look for the layers array in the rootfs section and determine the length of that array. It then returns it as the layer count : 2 entry as seen below. JQ is a very powerful tool with many capabilities that we don't cover here. Welcome back. Let's now learn about multi-stage builds in Docker. Typically, a Docker image is created using a single from command or source image. This is also referenced as a single-stage build, meaning only one stage or container is used to create the Docker image. We can obviously add anything to a given image, but each addition requires more space and can make the image more difficult to manage. Let's look at the Dockerfile for this build. We're using the base Ubuntu image, but adding the necessary programs for compiling the code, and then actually compiling it, and then running the final application. This leaves all of the code compile of the application in the container image, in addition to the development software that isn't necessary to run the program. This increases the size of the image and clutters the image unnecessarily. Note that in this case, compile refers to creating an executable program from source code. A multi-stage build uses multiple stages or multiple containers for different steps of the build to create a final container image. Typically, a multi-stage build has one or more build stages where data or binaries are prepared or compiled in some fashion. These components are then copied into a minimal final container image, saving space. The containers used in the build steps are then removed automatically. To accomplish this, Docker supports some additional syntax we've not seen in the Dockerfile yet. This includes the as alias on the from statement. It also uses the copy command with the additional -- from equals alias option. It's easiest to see how these work with an example. Let's consider our previous situation, where we need to compile an application prior to containerization. This time we are using a multi-stage build process to create the final container, but with a smaller, more efficient image as a result. First, we use the from Ubuntu command, but you'll notice we have as stage 1 at the end. This provides an alias or name for the stage. In this case, we're using stage 1 as the alias. Note that we could name this anything, but it's named this way for illustration purposes. Next, we have our normal build commands, which could include copying source files, updating packages, and actually compiling code. You'll next notice that we use a second from statement to define the base of our final image. In this case, we're using the Alpine base image. Now we use the copy -- from equals stage 1 /data -app /data -app command. This tells Docker to copy the /data app program from the container used in stage 1, where we compiled the code, and place it as /data app in the final image. We can use this to copy any data we want from any number of build stages as required. Finally, we set a CMD entry to the data app program and finish building the image. The entire build process is cleaned up, and the image used for stage 1 is removed automatically. Welcome back to our last video in this chapter, multi-platform builds. Our first question may be, what does multi-platform mean? It references two different aspects, an operating system and a CPU type. For different OS types, containerized applications usually use Linux, but could use Windows or Mac OS. Regarding CPU types, we usually see the x86-64 or AMD-64 type, the CPU instruction set behind most modern Intel and AMD processors. You may also see ARM64 or ARM7 chips, popular in cell phones, Apple devices, and single-board computers such as the Raspberry Pi. Usually the platform is defined as the OS type/CPU type, such as Linux/AMD64 or Mac OS/ARM64. Multi-platform builds use the concepts covered in multi-stage builds. The build stages use cross-compilers and rely on the platform of the host system. While it's possible to create multi-platform builds separately, such as for Linux AMD64 and Linux ARM64, it's not recommended. Note cross-compiler means compiling code to run on a platform different than this current host. The final stage of the build uses the platform for the intended target and copies any compiled binaries in place. Several options are used in Dockerfiles for multi-platform builds that define which container version should be loaded. The first option used with the build stage is the --platform equals $build platform option. $build platform represents the host platform for running the build. Assuming the base image is available for that platform, it should work automatically on different host platforms. Sometimes the Docker arg directive is used, along with a list of environment variables defined on the host. This is usually target OS and target arch representing the platform components of the destination system. An example is the line arg target OS target arch. We'll see this in a full Dockerfile shortly. Note the variables defined on the host can be defined in the shell or via the env command. Let's look at an example. First, we have the initial stage named build. The --platform equals $build platform tells Docker to pull the golang :1.21 image that matches the current host platform. We then use the workdir and copy commands to prepare the build container. Now we see the arg target OS target arch command, which passes in the target platform components. Please note these are defined by the specific command we enter on the command line of the host. Next, the command to actually compile the application is used. Note this is specific to compiling a Golang application, but the principle is the same for other programming languages. Notice that the target OS and target arch values are referenced using $ symbols. Finally, we create the final stage using the Alpine image and copy the compiled code from the build stage. To run a multi-platform build, we must use the docker buildx command rather than docker build. Docker buildx provides more commands and capabilities than docker build, including specifying destination platforms. The actual command used is docker buildx build --platform followed by the platforms, then -t, the image name, and a dot. This tells Docker to build an image for both the Linux AMD64 and ARM64 platforms. Note that Docker buildx also requires a new builder container present to build multiple platforms. This is done with the docker buildx create --bootstrap --use command. Don't worry about the details of this command, just note that it must be present prior to running a multi-platform build. Welcome back. In this chapter, let's discuss how to create multi-container applications using Docker Compose. Docker Compose is an additional command line tool for use with the Docker engine. It defines and manages multi-container applications. We'll discuss what this means more in a few minutes. Docker Compose can specify containers, networking, and storage volumes in a single file, compose.yml, or compose.yaml. You may also see older files named docker-compose.yml or .yaml. Docker Compose makes it very easy to share or demo applications by providing the Compose file. We'll create our own Compose files later. For now, let's look at an example and how to use it. Let's look at a simple compose.yaml file. Don't worry too much about the individual pieces. We'll cover this more in depth in the next video. As an overview, this particular application first specifies a container named web app using the web app image. This would be a custom web application housed in a container. This container needs to expose ports on the host, so the ports section shows a mapping of port 8000 on the host to port 5000 inside the container. Next, we define the other required component of the application, the Redis backend. If you're not familiar with it, Redis is a key value system used to store and retrieve data in a simpler form than a relational database. Our Redis container uses the Redis:\alpine image. To start an application, change to a directory containing the Docker Compose YAML file and run Docker Compose up. Note that on older systems, you may see Docker-Compose up. We can also specify a YAML file of a different name or location using the -f option with the name of the file. Note that if you need to use the -f option for an application, it must be used for each Docker Compose command you run. There is the option to start an application and detach from it, which keeps the containers running in the background. This is done with the Docker Compose up -d command. In this case, we run Docker Compose up and see that our two containers are created, and then the system attaches to them and shows us the output. In addition to the containers, you'll see that a new Docker network is automatically created. Note that your output will likely be different. This is shortened for illustrative purposes. To check on the status of a Docker Compose application, we can use the command docker compose ls. This provides a list of the applications, the status of the required containers, and the config file used to start the application. Let's consider if we want to shut down a running application. We can use the docker compose down command instead. Remember, if the -f option is used to start the application, it must be used to shut it down as well. This will automatically shut down any running resources from a given application. In this case, the Redis and web app containers are shut down and removed, and then the network created specifically for this application is shut down and removed. Let's take a look at how to create our applications with Docker Compose by writing our own compose.yaml files. Docker Compose files are written using YAML. Depending on your experience, you may be wondering what YAML is. YAML originally stood for Yet Another Markup Language, but now has the more amusing moniker of YAML Ain't Markup Language. It is a text-based file format, but whitespace indentation matters, much like Python. YAML is used in many development scenarios, often for configuration, due to its relatively human-readable format. The rules for writing or modifying YAML can be tricky, but maintain indentation as illustrated in examples. You can see this in the compose.yaml example, where Postgres: and pgadmin: are at the same level of indentation. A YAML skeleton will be provided when needed, but be aware of the formatting requirements if you need to create one from scratch. A Docker Compose configuration file can have multiple primary sections that handle different parts of the application. A primary section is left justified or not indented in the file. The services section is the only required component and lists all the containers required for the application. The networks section is optional and allows specific networking configuration used by the various containers in the application. A volume section is another optional area to define storage requirements for data shared between containers. The config section allows for specifying configuration details that would otherwise require a new container image. Lastly, the secrets section allows the user to configure any passwords, tokens, or API keys that the application might require. We'll cover a few of these in more detail, but they are all extensively documented in the Docker Compose documentation. The section we'll be using the most is the services section. This section defines all required resources that make up the application. This specifies the containers and images, along with the various settings for each container instance. There are extensive options available, but it's important to note that the settings only apply to the container they're specified on. Being defined in YAML, the sections are indented as required. The first subsection for each service is the name of the component or service, and the settings for each indented after that. Let's look at a sample services section in a config.yaml file. We first have our services section defined, followed by the resource name at the first level of indentation. In this case, we have a resource named Postgres. For the Postgres resource, we use a container_name option, which assigns a name to the container. Otherwise, the name is randomly generated, which can make troubleshooting more difficult. After that, we use the image option to specify which container image to use. In our example, we then show the port subsection, which provides a list of all mapped IP ports. In this case, we map port 5432 to 5432 in the container. The flow then repeats as needed for the remaining resources. Before we move to some practice exercises, let's review a few things. The first is that the config.yaml syntax is extensive. We've only reviewed a very small subset of the options available in a config.yaml file. Review the documentation for further details. Welcome back. We're getting near the end of our course, so let's cover one last new topic in Docker Compose: dependencies. So what are dependencies? Dependencies in Docker Compose define the order of resource startup. Resources, meaning containers, may require other resources to be in place first. Consider an example: a simple web application consisting of 3 resources. Our first resource is a database container running PostgreSQL, which must start prior to the others. Otherwise, the application will throw errors until the database is available. Next is the Python application that controls communications between the web and the database. Finally, the Nginx resource starts up the web server and actually serves the web content. Basic dependencies are defined using the depends_on attribute, followed by a list of the resources it depends on. Dependencies can be chained, as in our example. First, we define the PostgreSQL resource, which has no dependencies. The Python app then has a depends_on attribute listing PostgreSQL, followed by the Nginx resource, which depends on the Python app. In addition to a dependency chain, you can list multiple dependencies per resource if required. It's important to note that once dependencies are defined, the order of resources within the compose.yaml file does not matter. Important: when shutting down applications, the resources shut down in reverse order. In our example, the Nginx resource would be stopped first. Then the Python app resource is removed. And finally, the PostgreSQL resource is shut down as no running containers require it. Docker Compose provides other options for defining dependencies. The condition attribute tells Docker Compose when a dependency is successfully started and is ready. The first condition is called service_started, meaning the resource must have started normally. This is the same as the default behavior when using a depends_on without a condition attribute. The next condition is called service_completed_successfully. This indicates that a resource ran to completion before moving to the next resource. This isn't used often, but could be as a setup resource, a configuration validation, or anything where you need steps to occur before starting an application. The last and most powerful condition is called service_healthy. This means the resource is started and is not considered ready until it passes a health check. The health check is a defined method, such as accessing a specific web page or verifying a TCP port answers a connection request. Health checks can be defined in Dockerfiles or in a Docker Compose file as needed. We won't cover creating our own health checks in this course, but we can still use existing ones in our dependencies. Before we complete this video, let's look at some extra troubleshooting tools available within Docker Compose. The command docker compose logs will gather the output from all resources within an application. Here's an example application using Redis and a web application. Notice that the name of the resource is prepended to each line of the output. This would be the same as running docker logs container ID for each resource in the application. You can also run docker compose logs resource name, such as docker compose logs web, to get just the output from the web resource. Another useful tool for troubleshooting Docker Compose is Docker Compose Top. This shows the status of resources within an application. This example shows the same Redis and web resources with the name of the application, Compose Test. Welcome back to the last video of this course. We're going to cover a few outstanding details and review some of the topics we've covered thus far before finishing our last exercises. Let's review a task discussed earlier, sharing data between host and container using bind mounts. This is handled with the docker run-v command, followed by the host directory :container directory. For example, we can use -v ~host data /container data. One piece we had not covered previously is bind mounts can be applied in compose.yaml files as well. Under each resource directory, we can use the volumes option as shown. Under the volume options, we can use the list syntax in YAML, starting with a --host directory :container directory. As with above, we can use ~host data /container data. Note that list syntax here means each indented line starting with a dash. While we don't show it here, we can use as many entries as needed for all required bind mounts. As a reminder about adding containers to specific networks, we can use the --network flag with the name of the network. For example, we can use docker run --network net1 to connect a container to the net1 network. We can also define a network section in compose.yaml files under a resource. The name of a network is added as a section with other config options available, such as assigning a specific IP address. A quick review for port mapping. The docker run-p host port :container port will connect traffic going to the defined host on the port and send it to the container port and vice versa. A quick example is using -p 8000:8000. As with bind mounts, we can also map ports in compose.yaml files. The syntax is similar, with a ports option under a resource. We can then define the mapping using the list syntax with the -host port :container port. For the example above, we can use -8000:8000. We can map as many ports as required using the syntax, with one mapping per line. We covered some of this previously, but Docker Inspect provides information about provisioned containers, including stopped ones. To run the command, we use docker inspect ID or name. This provides various levels of information, including mounts for mounted data and network settings for information about the networking configuration of the container. The network section under Network Settings will show the name of the Docker networks the container communicates with and other details. In this example, the container would be connected to the Network 1 network. Let's quickly cover what we're going to build in the exercises ahead. We're going to create a basic multi-container data application. The first container consists of a Python web application that communicates with a database. We'll be using an embedded database for this example, but it could easily be a database on a separate container. Next, we'll add a data client application to communicate with the data service. The client is fairly simple, but could be easily expanded. All container communication will be over HTTP, but it could be done using a different protocol as desired. Great work going through everything in this course. Let's provide a few options for future study. Given the general purpose capabilities of Docker, it can be tricky to determine what to work on next. The first suggestion is to look through the extensive documentation available at docs.docker.com. There are many details and examples of various ways to implement Docker for your environment. Your best learning option is to containerize more applications, regardless of the purpose or platform. You can containerize custom scripts, services, and even games depending on your needs. Each behaves differently and can provide strategies to improve your Docker configurations. You can also create your own custom or private repositories to store your container images. You may wish to look at container orchestration platforms such as Docker Swarm or Kubernetes. These are multi-host platforms that provide options to run containers in a powerful, scalable, fault-tolerant way. If you're primarily a software developer, you can use Docker for continuous integration and delivery tasks. Finally, you can also look at using Docker with specific hardware such as GPUs. This can allow you to better utilize your hardware without requiring new setups for each application.